Well, thanks for coming to class today and wearing your Clinton sweatshirt. Graduated Clinton High School. That's all good, but it's life. So hey, thanks for coming to class. You guys are done. You guys are just done. Done. You just want to be done and be done. Okay. Well, today's kind of going to be a break from like normal, and this is just for your benefit. How's that sound? Basically, what we're at is for content-wise, you have a homework that in theory was due last week. I mean, so if you haven't gotten it done, get it in. I will get this graded and get it back to you. In addition, we have a lab that is due. When's the lab due? I don't know, the end of the week, Wednesday. You can give me. I mean, it's due when it's due. If you need time past Wednesday, let me know. But those are the only two things we should have left that are maybe out there. Homework 10 I think should be done, or homework 9 should be done. Homework or lab, the last lab is kind of the last thing that you got going here. And then we're going to do a final exam. I went over and gave you some final practice problems last week. And so today we're kind of in this one extra period where I could just send you all home. And honestly, if you want to go home, you can go home. Okay? And because what we're going to do is Wednesday, I'll post those example problems and we'll probably come up with solutions. The reason what I want to do today, though, is I kind of want to hit one last topic here on influence lines. I'm not going to test you on this. It's not on a homework. So if you want to tune out, you can tune out. The only reason I'm doing this lecture is because when you get to the FE, influence lines show up on the FE. So I don't cover them anywhere else, but I figure, you know what, I got an extra lecture here. It's one of those things that if we had more time, we might develop them more, we might go into them more. Influence lines, right? So influence lines show up in the FE, and it's one of those topics that I can probably cover in 45 minutes here, and at least get you set up so that if you see a problem like this on the FE, you've seen it before. Or if you're going to study for the FE and you're curious about it, at least you've seen it. Okay. So that's the point of this lecture today, is kind of just to help you, because a lot of you probably will go on to take the FE at some point, and if you do, hopefully this helps you out a little bit. If this lecture just confuses you, you can walk out and just forget it, and it won't impact your grade at all. It just might impact you and how you do on the FE. Okay. So this is totally just for your benefit, because I care about you guys and want you to pass the FE and that sort of thing. Okay. So what is an influence line? Actually, let's go back to what the FE says an influence line is. An influence line, what does it do? An influence line shows the variation of an effect, reaction, shear, or moment in beams, or a bar force in a truss caused by by moving a unit load across the structure. So let's think about that for a second. If we take a moving load, like on a transportation structure, you have a car going across a bridge, right? Let's say you want to put a connection in that bridge somewhere. You want to figure out, well, where is that car going to be where it's going to put the most shear on that connection? Where is that car going to be where it's going to put the most moment on that connection? Does that make sense? So the influence line gives you a graphical way to figure that out. So that's what it means. It shows the variation of an effect. So it shows a variation. It shows, like, if you move that load across this beam or across a truss, how is it going to impact the shear or the moment or the bar force in a truss? How's it going to impact it? Right? So that's kind of where we're going to start. I have another definition here that I got from somebody else as well that I'll throw down. But basically, the influence line is used to determine the position of movable set of loads that cause the maximum value of the effect. Okay, so that's what we're trying to do. We're trying to get the maximum value of that effect. So let me come back here, and I'm going to write a couple things down. Hopefully this will help. Maybe it won't, but actually, maybe I'll even pull from the FE definition here, because I kind of like it a little bit. This is also known as like a Mueller-Breslau principle, but I'm just going to start here, influence lines. Right, so in the FE reference handbook, the FE handbook, we're told that influence line, or I'm just going to put IL for short, shows the variation. I'm just going to copy this actually. The variation of an effect, and I'm going to put in parentheses reaction, because we can use them for reactions. We can use them for shear. We can use them for moment, or we can use them for a bar force in a truss. And we're going to look at both of these today. Caused by moving a unit load across the structure. Okay. So the point of this is to figure out that these are used, and the FE goes on to say that these are used to determine essentially the placement of the load that will cause the maximum effect. Okay. So before I go too far, let's just do it. Let's just do like kind of a case here to illustrate this, and then I'll give you another little principle of how to make it work. But before we go too far, what I want to do here is just give you kind of an idea. If we have a simply supported beam, right, and I've got somebody who just likes to run across this bridge just because, you know, they like to suffer. It's okay. I went for a run the other day, and my wife's like, "How was that?" I was like, I just walked in from like outside in the cold, and like I couldn't breathe. You ever do that where like you go from outside and like you're breathing hard to like an inside warm, like cold to warm, and like all of a sudden you cough and like you can't breathe? She's like, "How was it?" I was like, terrible. You know, it's like, what can I say? Like, I can't talk. Anyway, here's somebody who likes to suffer. He's running on a bridge. Let's say that bridge has some length, L, or you know, beam L. And as this guy moves or girl moves, you know, whatever, there's some distance x. So this is a distance x away from point A. Can you picture that? So for various values of x, right? So if we're, you know, let's look at, like, for this example, let's look at influence line for reaction at A. Well, what the influence line essentially does is it says, okay, well, if we have an x value, we can find like an AY value, and we can find an influence line value here. So for example, if x was 0, right, x is 0, what does that mean? It means this person, I'm going to say, has a weight P. So this is a person with a weight P. All right, this person is directly over support A. So how much is AY is holding up? All of P, right? So does that make sense? If x is 0, this guy's or girl is right over the A, so AY is taking all of P. Okay, if we're at, you know, for example, I'll come back to this influence line thing in a second, but if this person's all the way at B, how much is A taking? None, right? So if they're standing on B, A is taking 0. So I'm going to come, if X equals L, the influence line value at AY, I'm just solving AY. So I mean, just we can kind of do this. We know that if we solve it at B, the influence line value is going to be 0, or the AY value is going to be 0 because all the force goes right to B. So what do we do with an influence line? Well, we say we have a unit value of 1. So if we are, rather than the weight P, we're going to use a unit value of 1, and 0 times, 1 is going to be 0. Okay, but what about like L over 2? Well, at L over 2, how much of P is on AY? If this person's right in the middle, half, right? So P over 2. I mean, we could do this. We could do this. We could say, well, what about like 3L over 4, right? So if they were over here, we'd say, well, 1L over 4. Or if they were, at a quarter L, 1L over 4, we could say 3L over 4. So we could use the same principle. We could go solve these things. Or I'm sorry, this is 3P over 4. 3/4 P or 1/4 P. Right, and basically what we get here is 0.75, 0.5, 0.25, right? So if P was 1, this was the influence line is kind of like assuming P equals 1. So what does that mean? That means we have this chart here. Where'd it go? I'm going to put a chart. I'm going to just draw a couple lines down. But basically what we have here is an influence line for the reaction at AY. And basically what we're going to do here is we're going to start at 0, right? We're going to start at 0 and we're going to plot 1, the value 1. We're going to come out to all the way over to L. We're going to plot 0. And what you can see is this is just going to be a straight line down. So this is going to be 0.5. This is going to be our, 0.75. This is going to be like our 0.25. In this case, hopefully you can do in your head because it makes a little bit of sense, right? I mean, if this person's standing right at A, you take P times the influence line value, and you figure out, oh wait, if they're standing right at A, P times the influence line value, the reaction at A is going to be P. And you could use this chart. You say, well, if they're in the middle, we're going to say, okay, well, if they're in the middle, P times 0.5 is going to give us the reaction at A. Or P times 0.25, if they're over here, they're going to give us the reaction at A. So this one's pretty obvious. If they're standing right on top of A, it's going to have the most impact at A. Does that make sense? Okay. So what this leads us to is kind of an idea of how to. This is kind of like a brute force way of doing an influence line, okay? But there's easier ways to do influence lines, and I kind of want to go through that a little bit next here. So for influence lines, there's kind of a method to make influence lines, just like there's sort of an approach to doing shear moment diagrams. For influence lines, what we're going to do is to develop influence lines, we're going to add unit kind of displacements that correspond with what we're trying to find. Okay, so for example, what we just did was we were looking at a reaction. So for a reaction, right, we might have some beam here, right, but we want this reaction. What we're going to do is we're going to come over here and we're going to remove the support at that location, at the location of interest. So this is how, this is, you know, this is the reaction, this is how we modify it. And then the deformation that we're going to look at is what I said up here is we're going to apply a unit displacement. So if we want the reaction in the vertical direction, we're going to say, okay, let's look at a unit displacement in this thing. I mean, let's say maybe this had a pin on this side, okay? If this had a pin on this side, we leave the pin on this side, then what's a unit deformation look like? A unit deformation says, okay, we started with a beam that was flat, and what we're going to do here is we're going to apply a unit deformation of 1, and now we're going to take a look at this thing again. And that becomes our influence line. You see it? So what we just did here is we just basically solved for our influence line, right? All we did is we said, okay, we want to know about AY. We're going to take AY off, then we're going to apply a 1 unit deformation in the direction of the force, and that becomes our influence line. So our influence line is just this 1 unit deformation, right? And that's all it is it's this 1 up, and then it goes back down to 0 here because we know we're constrained by no deformation at the pin over here. Does that make a little bit of sense? So all we did was we took this out, we applied unit 1, and got our point. Okay, we could also have a couple other things. So we could also have, we could also be looking for shear. So for shear at a point. So we might start with some beam, right? And let's say we want to find shear, you know, at this point here. What we're going to do is we're going to modify this by adding essentially a vertical roller. So the way I'm going to show this here is I'm just going to put a roller kind of like this. Normally I only do 3, but this is we add a vertical roller. Okay, so if we still had our simply supported beam here, right, what's that going to look like? What's our deformation going to look like here? And this is where we have to understand our sign conventions a little bit. Our shear sign convention basically says this. If on the our shear sign convention says this. On the right side of the beam, it's going to go down. On the left side of the beam, it's going to go up. That's a positive sign convention. That's our positive sign convention. So that's what we're going to start with here. Right? If you remember when we drew our typical positive, the right side's down, left side's up, positive tension. This is our general positive sign convention. So the right side of the beam's going down, the left side of the beam's going up. So what does that look like over here? What that looks like over here is the right side is going to go down. The left side's going to, or I'm sorry, the left side's going to go down. The right side's going to go up. And if this is connected, basically what we know here is this total deformation is going to be 1.0. So if this is right in the middle of the beam, it's easy. It goes down a half and up a half. If it's not in the middle of the beam, it has to be proportional so that these slopes are the same. Okay. So that's kind of the idea with shear. And then lastly, for moment, right, we can start with this beam. And let's say we want to find the moment at this point. What we're going to do is we're going to add a hinge or a pin. So we allow the moment to rotate. Like here, we allow this thing to move up and down, like we allow it to shear. Here, we allow it to rotate because we're looking for the moment. We kind of release that moment. Just like in the moment distribution where we lock it, we temporarily fix it. Here, we kind of add an internal pin to release it. Okay, and what does the deformation look like? The deformation, we want to apply a unit rotation, which means basically what's going to happen is we're going to apply in a positive sign convention, kind of like up here. We're going to put tension on the bottom, compression on the top. This thing's going to push up. Okay, so we're going to push this thing up, and it's going to come up to, like, let's say something like this. It's going to have a unit rotation where if this is like theta A and this is like theta B, right? If I were to bring this out here, this whole deformation is 1.0. The whole angle is 1.0. So theta A plus theta B equals 1. And for small deformations, we can just work with it directly. So that's great, Mark. We sort of did it for this. How does that work out? How does that play out? What does that actually look like for something that's a little bit more complicated? Okay. Do you want to look at something maybe more complicated? Why not? Trying to think how much time I have here and what I want to do. Okay, let's start with an easier one and we'll go to a harder one. So let's look at that same beam that we started with, and let's say that we have a beam here that's simply supported, and what we're going to do is we're going to have some load P that can be moving across this beam, just like we did when we started. So this is going to be some distance x, and this total length, let's call it L. So if what we want to do is we want to find the influence line for moment at the center of the span. Right? I mean, intuitively, we don't really need an influence line for this, because intuitively, what do we know? We know that the moment at the center of the span is going to be biggest when P is at the center of the span. Does that make sense? But the influence line kind of helps us a little bit, and I'll show you a little bit why. Let's take a look at what that looks like here. So if we were to draw our influence line, what we're going to do is we're going to start essentially with this diagram, right? We're going to start with this beam. We're going to add this hinge in, and then we're going to push it up. We're going to push it up so that we get essentially a rotation here, right? So this becomes our rotation. And what we know here is we're going to have theta A, theta B, right? And we know that theta A plus theta B equals 1.0. Because it's symmetric, this makes it a little bit easier. Theta A is going to equal theta B. If we didn't know it was symmetric, we could also solve it and we could definitely solve it. I have that example here if you want to go over that one too. But if it wasn't symmetric, we could also solve what this is. But for small deformations, theta is going to essentially equal h over a. So what we want to find here is what this height is, and versus, so if we have h, we have theta, and we have a, we should be able to solve for h. Here we know this is L over 2 because we were told we want it at the center of the span. Right, so what's theta going to be? Well, in this case, theta A equals what? H over L over 2. Theta B equals what? H over L over 2. And because these are the same, you can see that these two are going to be the same. Theta A is going to equal theta B. But in other words, when we come back and when we plug these in, what are we going to get? We're going to H times over L over 2 plus H over L over 2 is going to equal 1.0. I don't like that L over 2 thing. I'm going to say 2H over L plus 2H over L equals 1.0. So what do we get? We get 4H over L equals 1.0. We get H equals basically L over 4, because if we multiply both sides by L, we get L over 4. You see that? Okay, so what does this mean? That means our influence line here is going to look like this. Our influence line we're going to come up to H over 4. I'm sorry, L over 4. This has a maximum value of L over 4. So if we said, for, let's say L equals 40 feet, this value here is going to be 10. If we had L equals to 40 feet. Why is that helpful? Well, if P equals, 60 kips, the person just got really heavy. Actually, it's more like a big fat truckload. Like, let's say it's a big fat truckload. I mean, we could do 60, we could do 40, we could do 20. But let's say P equals 60 kips, L equals 40 feet. The max moment at the midspan is equal to what? Well, it's basically equal to P times the max influence line value, which is P times what? 10. In other words, it's P times L over 4, or which is equal to what? P, which is 60 kips, times L, which is 40 feet over 4. Or really what it was, P times, there is 60 kips times 10 feet. So the max moment is going to be, what, 60 times 10 is 600 kip feet. Okay, it's a little convoluted, but let's just play this game for a second, because what we can do is we can also find, well, if the load P is at 10 feet, what's the moment? Well, instead of being 10, it's going to be 5. So 5 times P, 5 times 60 is 300. That makes sense? So it's like if I take this and we come back into visual analysis, I shouldn't have made it 40 feet. That's too long. Actually, no, I can't fit 40 feet on here, right? So if I make this 40 feet and I go to, instead of use vertical axis, I'm going to do, I'm going to make this a plane frame. I'm going to make this simply supported. Okay. I can put a load on this member I'm going to do a point load, a single point. I'm going to say minus 60 kips. So if my offset's 20 feet right now, that's right in the middle, and I can take this beam, and I can go to result view, member graph. What we see is the maximum moment 600, just like we found. But the other thing that we can find is that if I come back here and I say, well, okay, well, how is this influence if this is at 10 feet? What we just said is, okay, if this is at 10 feet, this value on our influence line is 5. So 5 times P, 5 times 60 is going to give us 300. So that should give us our moment here. So if we come back to result view, our maximum moment at the center, not at this point, our maximum moment at the center is 300. Again, this is just for the center of the beam, right? This is the influence line for the moment at the center of the beam. It doesn't mean it's the maximum moment at this point. Does that make sense? This point, just because the load's there, the maximum moment will also be there, but the moment at the center is going to be 5 times P. Make a little bit of sense, kind of, sort of. Let's look at one a little bit more complicated, then we'll go to trusses. So again, this is like a super brief. I wish I could do more, but like at least it sort of gets you in the ballpark, so that if you go to and want to study this stuff later on, you've seen it to a certain degree, and you can say, yeah, remember when Mattson didn't really teach that, and I didn't learn anything he said, but now I'm going to go study it for the FE. Maybe you'll care then. Okay, but let's look at this. Let's look at something like this where we look at this. So for the beam shown, and I will give you a beam, find the influence line for shear, influence lines for shear and moment at C. Okay, so let me draw you a beam here. In this beam, I'm going to start with a free end that goes to a roller, that goes to a pin. So this beam is going to look like this. Okay, and what we're going to have is, let me give you some dimensions here. So actually, let me give you some points too. I'm going to call this point A, this point B, the middle of this point C, and this point D. Okay, so what else do we want? We're going to call this 6. We're going to call this 4, and we're going to call this 4. And this is P, and it's going to move, it's going to move some distance X. I probably should have put the P on the other side, but whatever. It's going to move across the structure, across the beam. So let's start with shear. Shear is kind of a tricky one, but let's start with shear. So for shear, I mean, we could just brute force this, right? So if you were on the test, you could just brute force this thing and come back and just put shear at a whole bunch of points, or put that force at a whole bunch of points, and try to figure out, well, which one's going to make C the biggest. I mean, we could guess over here, we could guess over here, we could guess, a bunch of different places, and try to figure that out. I went and I think I made a model of this beam. I mean, we could look at a model of this beam. If I open it up, if it opens, let's see if it opens here. I put this beam into visual analysis, and we could take a look at it. Okay, so we could take a look at this beam. And basically, I have a 1 kip load somewhere on this beam, okay, somewhere on the beam. And if I go to my result view, right, I could take my result view and I could say, okay, I have a member graph, and at this point C, I have a moment of 1.5 or whatever it is. And I could do that for a whole bunch of moments. So I could come in here and I say, well, I'm going to put my force over here. I'm going to put my force, over here. I'm going to put my force, over here. I'm just going to keep moving that force. And so that force is walking its way along the beam, and I can just solve for the moment at every point. that just becomes a lot of statics. Does that make sense? It's just a lot of like going through and cutting sections and redoing and redoing and redoing, or making a lot of models and making this thing happen. The influence line kind of eliminates the process of having to kind of manually increment that load across the thing. Okay, so rather than manually incrementing that load across it, what we're going to do is we're going to come back here, and if you remember what I said with shear, was we're going to add this vertical roller. So we're going to come in here and we're going to take this thing. Let me just pull it down here. And at point C, I'm going to add a vertical roller. So I'll say add vertical roller at C. Okay, so what's that look like? Basically at C, we're going to have this vertical roller. We're going to have the beam. Everything else is going to be the same. So that got added in. And then this next thing that we're going to do is we're going to apply a unit deformation for positive shear. Okay, so what's this going to look like? Well, we're going to start with, I shouldn't have drawn it so dark, but basically we're going to, this is going to go up on one side. Actually, it's going to go down on one side. It's going to go down on one side. Right, so our positive shear says on the right side, it's going to go down. On the left side, it's going to go up. So on the right side, it's going to come down. So it's going to come down a certain amount over here. It's going to come up a certain amount over here. Now we have to connect the dots. The other thing is, after you apply the unit deformations, you keep straight lines. You have to keep straight lines. And if you can't keep a straight line, the thing doesn't move. But also we know that deformation's constrained at these points, at the roller and at the pin. So we're just going to come back in here and we're going to make it look like that. Okay. So this one's a little bit interesting, I guess, but if we know that this total distance here is 1, and we know this distance is 4 and this distance is 4, we know that we have to come up a half and you know, up a half and down a half essentially. So when we draw our influence line, now we're going to label these values here. It's basically going to be the same diagram. It's just going to be, we're going to have the points labeled. So I'm drawing this to scale, and it does help to draw it to scale to some degree. But because these are equal, we don't have to go through that theta A, theta B thing. This is going to be 0.5. This is going to be minus 0.5. Okay, and then the trickier part is, what's the value over here? This value, well, now we have to use similar triangles. Okay, so now if you see it, there's one triangle that looks like this, and one triangle that looks like this. Right? I'm going to call it 6 and H. So using similar triangles, we can say 4 over minus, or 4 over 0.5, or let me put it this way. We could do, say, H over 6 equals 0.5 over 4. So H, what does H equal? H equals 6 over 4 times 0.5, the 0.75. So this is 0.75. So in theory, what this means is the maximum shear at C will occur when P is at A. And the shear value at C when P is at A is equal to, so V of C for essentially X equals 0. P is at A, right? It's right over here. This is going to equal 0.75 times P, whatever value of P we have, times P. So can we prove it to ourselves? That's where I think visual analysis really kind of helps illustrate this process and kind of wrap it together a little bit. It's nice to be able to go back and forth a little bit from theory. And granted, you won't have visual analysis on the FE, which is just unfortunate. I mean, that'd be so nice if you could have visual analysis on the FE and you just plug things in. But let's come back here for a second. And what you can see here is I made some different load cases, 1, 2, 3, 4, and you'll see for one, the load is, I just put a 1 kilonewton or 1 kip force here right at A. As I go down here to number 2, I put it at the support, and then for 3, I put it at point C, and at 4, I put it at point B. So if we look at this, I can come to my result view. I can also go to my member graph, and you'll see this point right here is the shear at, this point is the shear at point C. You see that? Okay, so if I come to D1, so what's this? 0.75. That's what we calculated. That's what we expected. The shear at point C was 0.75. If I go to D2, that's if you remember, that was the point where it was right over the support. All the shear, there's 0 shear, which actually also corresponds with if the load is right at the support, we have 0 shear. If the load is right at point C, we're going to expect to get a value of 0.5. Okay, so if we come down here and go to, where are we? Wrong one, sorry. If we come back here and go to the right one and go to number 3, we get that value of the 0.5 and minus 0.5, depending on, this is a little weird with the signs, but it's 0.5. And then if we come back here to number 4, we go back to 0. Okay. So that kind of shows us, this influence line kind of shows us that the maximum force, shear force at this point is going to be when this is 0.75. And remember the signs, they were a little bit weird, but let's take a look here for a second and come back here. So I also put in a member load that's somewhere a little bit away from this point C. We would expect a positive shear at point C based on this load, right? So our influence line says if our force is somewhere in here, we're going to be like, instead of 0.5, maybe 0.375. Okay, and if we come back to here, this is offset. This is offset by like a foot from point C. So if this is 4 feet, this is offset a foot. That's 3/4 of 0.5. But let's look what we get. So if we come back here and go to our member graph and come back to this D, that's where our shear is a positive 0.375. It actually did work based on like this value, like right at this point. So if we were looking at putting the load right here, we get 0.375. Does that kind of make sense? So this influence line represents the shear at point C. So for any location where you place that P load, the shear at point C is going to be represented by this influence line. Okay. I'd ask if there are any questions, but I'm sure there are, and you guys are just brain dead. So, no, do you have any questions? I mean, like, is this making a little bit of sense? Like, it's kind of a screwy concept, but it works. I'll show you a truss one later. The truss one actually shows up on the, I think it's like if you buy the NTS FE practice test, the truss one actually shows up on the practice test. So I'll show you how to do a truss one. Let's do a moment one here first while we're still on this, but then we'll go to the truss. So we'll go to the moment here. So for moment, So for moment at C, I'm just going to redraw this thing kind of in here. What we're going to do is we're going to redraw this, but what we're going to do is, because we're dealing with moment, we're going to add a pin. So we're going to add okay, and then how is this thing going to rotate? This thing's going to rotate. Basically, what we know is it's going to have a unit rotation, and this is going to come up. It's going to come up to some point, but we're constrained by, you know, this point here. This can't move. We're also constrained by this point that can't move. So we're going to end up with something that looks like this. So again, if this is 4, this is 4. This total deformation here is 1. What we know is we have kind of like theta, and this actually kind of matches what we've already done to a certain degree. But what we know is theta equals h over a, right? So theta is h over a, roughly. For small deformations, it works. So in this case, we're going to see what's that mean. Because these are symmetric, we know that theta equals 0.5. So h here, so for theta equal to 0.5, symmetry. If it's not symmetrical, forget it. It's going to take longer. Okay, I shouldn't say forget it. It'll take longer, but basically we have 0.5 equals h over 4. So h equals what? 4 times equals 2. Okay, so if we come down here and draw our influence line, this is for moment at C. What's this going to do? It's going to come up 2, back down to 0, back down to 0. And then hopefully you can see what this value is here without having to do similar triangles. But if you need to, you could do like the height at A, you know, over. We could use similar triangles here, right? Just like we did before. So we have a similar triangle here and a similar triangle here. And if this value is 2.0, we could say that the height at A over 6 equals what? The height at C of 2 over 4. So the height at A equals 1/2 of 6, which is 3. So in other words, it's a similar kind of process. The max moment at C occurs when P is at A, right? Because that's the biggest value on our influence line. I could say the max negative moment because this is negative. The max positive moment occurs when it's right at C. Okay, but the max negative moment occurs when P is at A, when it's over at this point. So the max moment value, so M max equals -3 times P. Okay. That's when, you know, P is at A. So we could prove that to ourselves. We can come back to visual analysis, and we can prove that to ourselves here. So if we come back to visual analysis, and again, the loads, the way these loads are set up is 1 is at A, 2 is at the support, 3 is at, you know, C, and 4 is at the support. So if I come back to my result view or member graph here, what you see is this moment when we have the moment, you know, occurs at point C. When the load is all the way over at the left, we get 3. When the load is at the support, there's 0. When the load is at point C, we get 2. And when the load is all the way at the other support, it's 0 again. And then we could go somewhere in between, and we could say, well, if the load is way over here, we get 1.5. Okay, a little bit less than 2. So again, it's the influence line is kind of. I wish I had more time to like give you a homework assignment on it and that sort of thing, but like you'd probably understand it a little bit better. But like it's just this graphical approach of how to solve for maximum shear or maximum moment at a particular point. Okay. So let's look at trusses. Trusses, this is the type of problem where, could you see it on the exam? I wouldn't be surprised in the sense that the NCS practice exam has one of these. So it's worth looking at, right? But basically, let's say that we have a truss, given. Let's say we have a truss, and I'm going to make this truss relatively simple. I'm going to put 4 feet. So I'm going to make how many? I'm going to make the truss look like this, okay? Everything's 4 feet except for the diagonals. That's 4 squared to 2, okay? And I'm doing that just to make it a little bit easier, but let's take a look at this. So if this is our truss, and let me make it simply supported here. And let's say that we have a car or some little something that's pretty small. If this is 4 feet, but this thing's going to move across the bridge. Okay, I mean, we can make these 4 meters if we wanted to. Let's make them meters. That probably makes a little bit more sense. It doesn't really matter, honestly. The units don't matter so much. But let's make these 4 meters just to make our car to scale a little bit better. And then vertically, we're going to say 4 meters as well. And we haven't really talked about how to do influence lines for a truss, but let's start with which member do I want to start with? Let's start with member. Let's find. Let's do this. Let's find the value of x that will make member CH that will. Okay, so let me label these points. I'm just going to go across the bottom, A, B, C, D, E, F, G, H along the top. So what I'm going to say is let's find the value of x. This is the member that we care about, CH. So this is going to go some distance x, right? It's going to move some distance x. What distance x will cause that member CH to equal 0? Okay, so we're going to use an influence line to solve this. So first, we're going to find, so step one, we're just going to solve, use an influence line to solve, or solve for, probably should have written solve for the influence line. But basically, to solve for the influence line, if we think about a truss for a second, this force, right, is going to be placed kind of at one of these nodes, kind of always. Or it's going to be transferred to one of those nodes, or some combination of those nodes. Like if it's in between, right? If it's in between, half of it would come this way, half of it would come this way to evaluate that one, right? So all that we really care about is at the node. Does that make sense? But for trusses with a point load, basically what we want to do is we want to solve the truss with the load on either side of the member. And what do I mean by that? What do I mean by that? What I mean is step one is well, let me put it this way. If this car is right at point A, all the force is going to go to point A. CH is going to be 0. And I'll put not at support. Okay. So X is, so in other words, X is greater than 0 and it's less than 16 meters. So we have to find some value out here where this thing is going to be. But at the support, we know it's going to be 0. At the other support, CH is going to be 0 because all members are going to be 0 if it's at the support. Okay, but what we want to do is we want to say, okay, we're going to take this truss and now we're going to solve it. So step, kind of one here is we're going to solve this thing. If we put that, force right here. So if we put that force, if this is one side of C, we're going to put that force right here. So I'm going to say I'm just going to start with a 1 kip force here. Okay. And I'm going to put it pulling down, and it doesn't matter. It just shows up better down here. So this is kind of like step one. This is saying apply 1 kip force at C. Okay. If we do that, what do we know about these two reactions? Can you do them without summing moments? What are they? Yeah, 0.5, a half, right? This is symmetric, so it's just a half and a half, right? So those are our reactions. And can you solve for this member force pretty quickly? In other words, do you know how to do method of sections without struggling through it? So if we draw a section, right, what do we have? Our section is going to look like this. We're going to have 1/2 a kip up. We're going to have some force here, which is CH down. We're going to have some force here, some force here. But really, the other thing that we know is this is going to be CHY, and this is going to be CHX. That makes sense? Do you remember how we solved this problem? Sum of the forces in the y direction equals 0. CHY equals 1/2 a kip. Remember that? That's in tension. That's positive. So what does that mean about CH? Do you remember what CH equals, or do you have to do your triangles? The triangles for this one are pretty simple because what we know is we have 4, 4, and 4 square root of 2. Right? Make sense? Because there's a 45-degree angle, 4, 4, 4 square root of 2. So what does that mean here? It means CH, therefore, what we have is if we do our similar triangles and we say CH, CHY, and CHX, we're going to say, well, CH equals essentially CHY times the square root of 2. The 4's will drop out. So CH equals what? Is that 0.70? No. 1/2 times point. I can't think. I can't. Let's find it. 0.5 times square root of 2. Yeah, it's 0.707. Square root of 2 over 2 is 0.707. That makes sense. Okay. So that's for case one when P is at C. Okay. Does that make sense? That's 0.707 kips. Everybody okay with that? Do you remember how to do method of sections? If not, this is a good review for the test, the final. At least this part of it is. And would you be expected to do something like that quickly or could you be expected to do something like that quickly on the FE? No doubt. Like, I would not be surprised if you get some sort of trust question and you have to solve a member force pretty quickly on the FE. No question. Like, that's a 3-minute question. This whole influence line question, it's more than a 3-minute question because you have to do it again. Okay. you have to next, what I said is solve the stress with load on either side of the member. So we started at C, then we're going to go to D. Okay, and we're going to go, so next we're going to apply the 1 kip force at D. Okay, so let's do that again. And if you want to practice, you can solve this thing hopefully fairly quickly, maybe even before I'm done drawing it out. But let's take a look and see. So what I'm going to do is I'm going to apply this force here. So what does that mean about my reactions? What are my reactions? If these are all equal, do you remember anything that we just did about that influence line for the reactions? How much is going to be on this side? How much is going to be on this side? We're going to get 3/4 on this side and 1/4 on this side. Right? I mean, you get some moments about point A and solve it if you want, but hopefully you're starting to get to a point with structural analysis where you can kind of see beyond, I need to apply a sum of moments equation. You can sort of start to see the answer. Does that make sense? It's like, this is just a ratio of, what, 3 to 4, right? 3 comes to here. This distance is 3, and this distance is 4. I shouldn't say that. This distance is 3 times 4 meters, and this distance is 4 times 4 meters, which is, what, 12 meters and 16 meters. But you can see that ratio of 3 to 4 gets us over to this point. Okay, so then what do we do? Then we have then we have the same thing, kind of, sort of, but now we have what? We have 3/4 up. We get 1 kip down. We have these different forces here. So we have CH, CHY, CHX. So again, all we're doing here is we're summing forces in the y direction equals 0. What do we get? We get minus CHY minus 1 kip plus 3/4 of a kip equals 0. So if we put the CHY on the other side, we get CHY equals minus 1/4 of a kip. So what does that mean? It means it's out of tension, now it's in compression. Right? So what does that mean? It means CH equals minus 1/4 of a kip times the square root of 2, or CH equals, what's that work out to be? Minus 0.25 times the square root of 2 is minus 0.35, like 36. I mean, it's some value, but this is in compression. And you'll notice here that the thing that I kind of want to point out here is what happens when we move this load from, from joint C to joint D. What just happened? It went from tension, 0.707, to compression. So what has to happen in between? If it goes from tension to compression, it has to go to 0 at some point. Does that make sense? So let's draw our influence line next. So our influence line for that truss for, member, what's this, CH, is going to look like this. We're going to have an influence line that is going to look like this. Hold on, let me just get the points drawn in here. I'm just drawing 4, this is every 4 meters essentially. So what we're going to do is we're going to start at 0 and we're going to end at 0, because if the force is right over the support, there's going to be 0 force in CH, okay? And then what are we going to do? When it's at C, when it's in the middle, we know it's what? It's 0.707, 0.7071. So we're going to come up, when it's up here, we're going to come to 0.7071. And then when it's at point, what's this? At point D, it's minus 0.0.3 0.3536. And all we're going to do here is just connect the dots. So what we're trying to find, so that's the influence line. So if we place that force anywhere along that bottom chord, assuming the force will transfer kind of proportionally to each side, we're going to be able to figure out what the force in that member is, if it's placed anywhere along the bottom of that truss. Does that make sense? So if it's placed at the support, the member in CH is going to be 0. If it's placed at point C, that's going to give us our maximum, which is going to be 0.707 times whatever the value is. If it's placed here, it's going to give us our maximum compression value. And if it's placed here, it's going to go back to 0. So somewhere in between, we're going to be able to get that value. And what we could do is we could use similar triangles here to figure that out. So let's use our similar triangles. So find, the distance, I'm going to just call this D. Let's find this distance D, right? This is the distance D because ultimately we want this value X at which this point is 0. So what's D? Well, again, we have to look at similar triangles, and similar triangles you probably hate similar triangles after this class, but we've got one triangle there. We've got another triangle here that we know all the information on, right? So our two triangles look like this. We have one triangle that goes from D to 0.7071, and the other triangle goes 4, and what's 0.7071, plus this one here is going to be 1.0607. Right? So if we want D, I'm going to say, well, D over 0.7071 has to equal 4 over 1.0607. So if I take this and multiply it by 0.7071, I get 0.75 D, 0.75. So the question is, does it work? I sure hope so, because that would be like a terrible way to end the class if it didn't work. I actually didn't put it in yet, so this is going to be, let's see if it works. I don't know. Let's go for it. Let's see if it works. Okay. So let's go and see what happens. So I put this truss in to visual analysis, and what it looks like is this. And it sort of looks like this, but let me delete these members just because they're not really needed, and it'll hopefully make things look a little bit better for you. So okay, so this is our truss, and just like before, what I did is I put this point load, this one kip starts over here, and then if I go to D2, it goes to the middle, and then if I go to D3, it goes over here. You see that? So I'm going to come to my result view, and specifically, I'm going to look at this member. So D1, you might be saying, wait, 0.35, wasn't that supposed to be negative? And if you remember, D1, where's the point? The point is right over this point, so we get the 0.3535. Okay, when I move it to 0.2, I get the 0.7071. When I move it to 0.3, I get a negative, now it's an compression, negative 0.353. Okay, and that's pretty cool, because what this diagram does is it shows us the force in that member wherever P is along the bottom of the truss. Okay, and it's kind of a cool thing, but what we could do is we come back here, and instead what I can do here is I can come to D. Let me just come to new load case. I'm going to apply a member load. I'll do apply member load. I'm going to say I'm going to do a point load, a shear. I'm going to say -1, and I'm going to do an offset of 3. Okay, so this is 0.75 away from over here, and if everything worked out, I really hope it did. we get almost 0. Oh, come on. That'd be so nice if it was actually 0. It didn't work out to 0. And that makes me sad. Well, I guess I'll need to go figure out why I didn't go back to 0. I'll go figure that out. And, oh man, really? That's killing me. Okay, I'll need to figure out why this didn't go to 0. I'll figure that out, and we can talk about it next time in class, and then we'll finish our review. So that's it. So anyway, that's it for today. I wish it ended better because that would be so much nicer. But man, I gotta go troubleshoot this. I will troubleshoot it. It's probably something really simple. We'll talk about it more on next class. But if you have questions on moment distribution, let me know. Finish the homework up, finish the lab up, and we'll go from there. All right. Thanks, guys.